Okay, welcome everyone. Today's speaker is Dr. Thomas Beatty. He's an assistant research professor at University of Arizona in our department. He received a PhD at Ohio State with Scott Gowdy. Is that correct, right? And then he had a postdoc at Penn State and became an assistant research professor there. And then we recruited him to here as an assistant research professor. So today he's going to talk about the exoplanet atmospheres, which he's was working on, the Roaring Twenties. So now, Thomas, the floor is yours.
Okay, thank you. Thank you all for coming. So I'll say just as a little bit of a preface before I get into this, that this is going to be, so I'm using this as a little bit of an excuse to do a dry run of a sort of more general talk about exoplanets. So I think for this crowd, I'm going to have a little bit at the front that we all know, because now that the pandemic's ending, I'm starting to do more of the talk circuit. So thank you for bearing with me as I try this talk out on you all for the first time. Okay, so the Roaring Twenties, hopefully not followed by a similar ending to the original Roaring Twenties. But I chose this title because, as I'll talk about, over the next few years, instrumentation that's coming online, particularly with JWST, is really, I think, going to significantly alter our understanding of exoplanet atmospheres and what it tells us about where exoplanets come from. So I wanted to begin just by highlighting a bunch of the people that I work with and have worked with on a lot of the things that I will talk about in this talk. None of this happens in a vacuum. So a lot of this work has been significantly aided by all these people on this list. So I like to start actually with a picture like this and think about the idea that I would say literally for thousands of years, right? People have thought about planets around stars up in the sky. Is there a planet like the Earth around other stars? And I think at this point, we now know the answer to that pretty well. We now know from exoplanet demographic studies that planets like Earth are relatively frequent, and exoplanets in general are pretty frequent around stars like the Sun. And now that we have that information, we can really start drilling down for the first time and understanding more about exoplanets and where they came from, and even answering questions about habitability that we couldn't even a few years ago. And so we're really standing on the edge of this, as I said, this revolution in our understanding of exoplanet atmospheres and our understanding of the place of Earth and life on Earth in the overall context of the universe and the population of planets and stellar systems around us. So I like to begin while I still have everybody's attention, because I know particularly over Zoom, everybody's mind sort of wanders, with my conclusions, just to make sure you get these takeaways from this talk. If you remember nothing else, these 4 bullet points. So as I said, we now know for demographic studies, exoplanets appear relatively common. What that means, one, is we know that we have a lot of targets for atmospheric characterization, but 2, if they're common, that means we have a lot of parameter space to explore to understand planet formation and planetary habitability. Second point, currently, I would say the major uncertainty in our ability to understand both those questions, to measure abundances, is our uncertainties about the cloud properties of exoplanets and how those change our ultimate abundance measurements we get. But we're working on that. And as I'll describe, and going forward, JWST should provide us with almost an order of magnitude increase in our ability to conduct abundance measurements modulo those cloud uncertainties. So we're going to get much better information about planet formation pathways and possibly habitability. And finally, I'm going to conclude this talk by talking a little bit about some more speculative, well, not speculative work, some work that I've been doing with some people at Goddard and elsewhere on looking for technosignatures. So expanding our thinking about habitability and searches for life and biosignatures to also include technological evidence for life and technosignatures, and making that not about looking for UFOs, but placing really firm astrophysical constraints on what do we expect to see and what should we be looking for to make sure that we see it. So as I said, we now know about over 4,000 exoplanets. And this diagram, actually, when I was making this talk, I made this diagram on Saturday. And I mention that only because I feel like whenever I remake this talk, I need to remake this diagram, even if I'm doing it 6 months later, because the rate of discoveries has remained pretty constant and pretty high for the last several years. So we now know of over 4,000 exoplanets, really filling out this period mass diagram. And what this means is we now also have a really, I'd say, a decent understanding of exoplanet demographics. Now, that's not, I'm sure there are some people in the audience who are sort of twitching at me saying we have a decent understanding of exoplanet demographics. But I would contend that at short periods, say less than 100 days, and for large planet radii, say super Earths and up, I think we have a decent handle on what's going on. Now that gets fuzzy at longer periods, that gets fuzzy at smaller radii as we reach the limits of our detection sensitivity. But I think we're getting a much better understanding, certainly than we did even 10 or 15 years ago today, about where exoplanets are, how frequent they are, and what kind of planets we can expect. And this is already telling us things about planet formation. Right, so this is a paper from B.J. Fulton showing this the Fulton radius gap. How planets, as they form, the hypothesis here is this gap is caused by planets that either do not accrete a significant gas envelope after they've accreted a solid core, or they do accrete a gas envelope. And in between those two extremes, there's a valley where you either go or you don't. And if you don't go, you stay on one side. And if you do start accreting significant gas, you jump over to the other side. So we can see some of the properties of the planet formation process in these demographics. But we want to know more about the exoplanets. We don't just want to look at their frequencies. We want to actually look at what the exoplanets themselves are doing. And only a small subset of all these planets have actually received spectroscopic atmospheric measurements. So here they are in red, and you can see most of them are hot Jupiters. Those are the easiest to observe, but there is a small subset of Earth, super Earth, Neptune-sized planets that have received detailed atmospheric characterization. So we're really just beginning our work on understanding the atmospheres of exoplanets in detail. So why study exoplanet atmospheres? What do we get out of this? Well, I would say that we get, roughly speaking, two general things that we learn from studying exoplanet atmospheres. One, studying them and measuring their properties lets us better understand how exoplanets form. The exoplanets we see today are the outcome of the planet formation process. They're the endpoint of planet formation. That means that if we understand what their current properties are, we can in many ways backtrack how the formation process had to work. From ALMA observations and things like that, we have a pretty good understanding, or we're getting a better understanding of protoplanetary disk properties. By looking at exoplanet atmospheres, we know what the outcome of those disks collapsing into planets is. And we can use those two anchor points at the beginning and end of the formation process to try and work out what must have happened in between. Second, we can, learn what makes a habitable planet, right? Why does Earth become Earth and Venus become Venus? I would say that is not very well understood. How the exact location, the exact composition of a planet determines whether or not it becomes a habitable planet or not. And we can actually look for life, right? The big question that a lot of this is leading to, is there life elsewhere in the universe? And I'll say that both these were called out by the recent decadal. In particularly, searching for life was designated as one of their priority areas. But understanding planet formation was also punched out as an important field to consider for the next decade. So how do we actually do this? So for planet formation, generally what we look for is one, trends in bulk abundances. That's shown on the left. The expectation is that for Most planet accretion scenarios, where planets form via accretion instead of gravitational instability, that the bulk metallicity of an exoplanet will increase as the planet mass goes down. Pretty much as the planet mass goes down, you're mostly composed of these pebbles and solid material that's accreting, and not so much the gas, the hydrogen helium gas in the disk. Second, we can actually look at the specific elemental ratios in the planetary atmosphere. So not just the overall metallicity, but specifically, what is the carbon to hydrogen ratio? What is the nitrogen to hydrogen ratio? C, N, and O are very important to understanding where the planet formed, because if you form initially at different parts of the protoplanetary disks, you have different elemental ratios, and that's reflected in its present day abundances. For planetary habitability, as a start, the first thing we would want to know is there water and oxygen on in the atmosphere? Is it an Earth-like, Earth-sized planet? And is there roughly an Earth-like atmosphere with some amount of water and some amount of oxygen? Oxygen in particular being one of the main biosignatures that we would look for evidence for life. So in both cases, what we want to do is we want to measure the atmospheric composition of exoplanets. Right, both for understanding planet formation and for understanding habitability and searching for life. Fundamentally, what we want to do is we want to use spectroscopy to measure the spectroscopic composition of exoplanet atmospheres. The way we do this, and again, as I said, this is for sort of a general audience, so forgive me, this is outside of my talk flow now for doing this background for you guys. The way that we do this is generally using transmission or emission spectroscopy observations. So for transmission observations, diagrammatically shown on the left, this is the planet is transiting in front of the star. The starlight is passing through the upper edges of the atmosphere and spectroscopically imprinting on that starlight. Emission observations, usually in secondary eclipse, we're actually seeing light coming off the planet directly. These transit transmission observations generally probe high up in the atmospheres, pressures of less than a bar, and also just near the terminator of the planet. Eclipse observations go deeper in the atmosphere, down to about a bar, and they're also integrated across the entire day side. So both of these are also showing different areas of the planetary atmosphere to us. One way we can see the global atmosphere is by using phase curve observations and watching for an entire rotation of the planet. That also is emission observations. It shows us down to about a bar, and it gives us emission as a function of longitude. The way these observations look, they give us two different ways to look at exoplanet atmosphere. So I've already said we're looking at different areas of the atmosphere. Transmission is around the terminator, emission is integrated across the day side. They also just appear very differently. For transmission observations, if we're looking at these plots, an absorption feature in transmission is a bump upwards. That's because the absorption, it is absorbing more light. The planetary radius apparently increases from our spectroscopic vantage point. And so an absorption feature in transmission is an upward feature. Emission is a downward feature, more like what we're used to seeing with other astronomical objects, stars, and galaxies. I'll also say that one result from the demographic studies is that direct imaging of exoplanet atmospheres is going to be difficult for the foreseeable future. Most of our current ability to directly image exoplanets can mainly be done at relatively large separation and relatively large planet to star contrast ratios. So we'll likely have to wait until the 2040s with the launch of WFIRST or a follow-on HabEx or LUVOIR to really drill down and get good measurements of exoplanet atmospheres using direct imaging. So for the next 10 or 20 years, we're mostly thinking about these transmission, or the eclipse observations as our primary method of measuring what's going on in an exoplanet atmosphere. Okay, so having said all that, the big elephant in the room, clouds. We know that clouds are present on all planets that have atmospheres in the solar system. Jupiter has these beautiful clouds, is taken as this image from orbit. For exoplanets, our problem is we're thinking about measuring exoplanet abundances, is that different cloud models can yield different abundance measurements. So this is the same transmission spectrum that I worked on with Nicole Cologne for KELT 11. So this is a Hubble transmission spectrum. And you can see for different cloud models in the blue and the red and the yellow, we get very different constraints on the overall bulk metallicity. You can see that on the right, and the C to O ratio. So different cloud models give us very different abundances. That means we need to understand what is happening with clouds on exoplanets if we want to be able to measure the abundances precisely. And I will say that Spitzer infrared observations have shown us generally that at least night-side clouds appear universally present on giant exoplanets. So for hot Jupiters, usually people conceptualize them as not having clouds, but actually these observations have shown that it does appear that even for hot Jupiters, night-side clouds are certainly present universally. The way to interpret this is that the day sides are clear on hot Jupiters. They're too hot to have clouds on most of their day sides, but the night sides are all at a fixed temperature of about 1,000 degrees over a wide range of parameter space, i.e. there are clouds that are present that are clamping these night side temperatures to about 1,000 degrees. Modeling that's been based on these observations have shown that these are probably silicate clouds. That's about the right temperature and optical depth to cause this feature. So it looks like some form of silicate clouds are present on the hotter exoplanets on their night sides, and that generally we should be thinking about clouds on all the exoplanets we're looking at, not just the cooler objects. As a result, there's now whoops. All right, good. This is why I'm doing this dry run. This is from an older voice track on here. Okay. So there's a substantial effort now to include these cloud physics in 3D climate simulations in GCM's 3D climate models. There are a couple of outstanding hurdles to overcome here, though. So one, at the moment, there's significant uncertainties in the cloud physics for these atmospheres, particularly the microphysics. I'm talking about things like the KZZ, the vertical diffusion coefficient, and just like grain size distributions. All the great microphysics that you can think of is, I would say, not understood well enough to really nail these to the wall. Secondly, from a computational standpoint, it's also can be difficult to include clouds in GCMs. So usually this means the clouds are included via post-processing. The GCM is run, you get a stable solution, and then you add clouds on top of that. That means that we are not well simulating at the moment horizontal transport, meaning clouds blowing from the night to the day side, or radiative feedback, clouds self-shielding parts of the atmosphere and causing more clouds to form. So there are significant uncertainties still present in GCMs that the people are working to overcome. Okay, so one thing we can do is, can we map the clouds? How do we actually characterize some of these cloud properties? So I'll talk a little bit about, oops, picking up this audio track. So I'll talk a little bit about these observations. These are Hubble WFC3 observations of a transiting brown dwarf, Kelt-1. We observe spectroscopically over an entire orbit. So we get spectra of the brown dwarf over the course of its entire orbit, and we can look at how this spectra changes. So what is spectral? So the Eclipse Spectrum is consistent with blackbody emission from the day side. We've seen this a lot in other hot Jupiters. That we look at the eclipses of these very hot Jupiters, and it looks like a blackbody flatline eclipse spectrum. The morning spectrum is also blackbody-like. We get a very nice flat line in the morning at about a longitude of minus 45 degrees. And remember, these are all hemispherically integrated. So when I say the day side, that's across the entire day side. The morning is part of the day side, part of the night side as well. But the spectrum at the peak of the phase curve, which occurs in the middle of the afternoon, is not a black body. There's actually, we start picking up a significant water absorption feature at this longitude. So the spectrum coming off of Kelt-1 is changing as a function of longitude. Our interpretation for this is that this is showing us variable cloud cover over the day side. That the black body-like features, the flat spectra we see in the morning, is caused by gray clouds, roughly gray clouds being present in the morning. They obscure this water absorption feature. And then over the course of the day, the clouds are burned off because the day side is much too hot to support them. And as this water absorption feature increases, the clouds are dissipating. And then we see the water absorption feature go away as we go back to the night. The clouds reform on the night side. So we can construct this cloud map of what Kelt 1 looks like. And we can see that in many ways it imitates these post-process models. We have strong clouds on the night side, and the post-process models do not have significant clouds on the day side. But we do see significant clouds on the day side from these. Sorry, I'm jumping around because I'm trying to avoid the vocal track, but it's giving me a hard time. So what this means is what we're seeing evidence for this horizontal transport. Remember I said that in these GCM models, it's very hard to include horizontal transport because the clouds are added after the fact. The fact that we're seeing significant clouds on the day side, in the morning in particular, where temperatures should be too hot for these clouds to exist, indicates that these clouds are being blown over onto the day side. Meaning that even for hot planets, we have night side clouds, and we even have some clouds likely on the day side that are being blown over from the night side. So even on the hot planets, we need to be thinking about what are the cloud properties, how are they affecting our abundance measurements, both in transit transmission spectra, where we see the terminator, we see these thick sort of the edges of the night side clouds, and even on the day side, where ostensibly the day side should be clear, but in reality, there likely is significant cloud coverage being blown over, particularly onto the morning side of these planets and affecting our measurements and affecting our abundance measurements. Another thing you may ask is there cloud-driven variability? We now have all these clouds blowing over onto the day side. Is there weather on these planets? We see weather on Jupiter, we see weather on Earth, obviously. So if there's all these clouds, can we see variability? And this is important too, because often, these atmospheric measurements are relatively time intensive. And so often we will just observe once. We'll observe a target once and we'll get a result. And that is the result we get for that atmosphere. But if there's significant variability, that means that the result we get for that atmosphere when we observe once is not the equilibrium state of that atmosphere that we can use to model the entire atmosphere. What we're actually seeing is the equilibrium state. And on top of that, we are seeing the weather on the day that we observed. We're not necessarily seeing right down to the equilibrium state. So we need to know if there's significant variability in these atmospheres driven by these clouds if we want to really be confident in our ability to measure the atmospheric abundances or know how much we need to account for this. So I'll say that early theory did predict significant variability in exoplanet atmospheres. This is a paper from Emily Rauscher showing different Spitzer phase curve observations at different wavelengths. That's the color coding here. And you can see the thing to note here is that this is not, the amplitude in an individual color is not constant. There's significant amplitude variations as a function of even orbit to orbit predicted early on in these Spitzer phase curve observations. And work that I've been doing with a grad student working with me, Matthew Murphy, who's been analyzing repeated Spitzer phase curve observations of WASP-43, which we know from other observations should have pretty significant clouds on its day side, meaning it should be a pretty good target for these sorts of variability observations. Matthew's work has shown that over 3 Spitzer phase curves separated by about a month on one end and 5 years on another, that over the course of these 2 different time scales, the best fit observation is one where all the phase curves, the phase curve stays constant. There's not a significant amount of variability in WASP-43's atmospheres over these timescales, over an orbital timescale, over a month timescale, or even over a several year timescale separated by this. The modeling that Matt's been doing to try and get a better physical intuition for this shows that we can also constrain the cloud thickness variability. So we do need to include clouds to model the phase curve, the overall phase curve from WASP-43. And the overall cloud thickness appears to be remaining pretty stable, right? Because we don't see any we don't see any photometric variation over these observations. So at the level that at least Spitzer can show us, it does not appear that at least giant exoplanets show significant variability. This is a good sign for later observations with JWST. So we're now beginning to have a better understanding of clouds on exoplanets. Right? We now understand that they're generally present. We now understand that even on the hottest planets, that some of them are being blown over onto the day side. We need to account for them in some manner, but that at least at the limits of current precision, that any potential variability caused by these clouds appears to be minimal. We can't see it yet. But particularly as we think about moving towards JWST, we do need to get better information about the cloud extent, right? How far up does the cloud extend in the atmosphere in particular, and what's going on with the microphysics? What is the vertical diffusion coefficient? What are the grain sizes? That's going to influence significantly the abundance as we get out. So that's one task to work on in the next couple of years, is better understanding the extent and the microphysics in exoplanet clouds. All right, so let's talk about JWST. Thankfully, it's launched, it's in orbit, everything is going well. I think there's a bunch of people on this call who are on one or other of the commissioning teams. I know I get questions on calls I'm on about, so how everything seems like it's going super well from the outside. How are things from the inside? Things are going super well from the inside too. I mean, there are sort of the usual hiccups, but nothing nothing earth-shattering. Everything is rolling along, I think, as well as anybody could have expected at this point. So observations of JWST, right, are going to provide us with almost an order of magnitude improvement in terms of, the combined wavelength, precision, and resolution that we get from these. We're going to be measuring over much atmospheric properties over a much wider wavelength range. We're going to be measuring it with a much higher precision than currently possible and at a much higher resolution. That means we're going to get significantly better constraints on abundances, both in terms of bulk metallicities and in terms of elemental ratios. We're going to do way better than any of our current measurements using JWST. Modulo these cloud uncertainties that I was just talking about. And I've shown here on the right all the different instruments that we can use to do exoplanet time series observations of JWST. There's NIRISS, NIRSpec, NIRCam, MIRI. All the 4 instruments have a mode to do these observations. I'm going to talk in particular about NIRCam, since that is the particular instrument I'll work on. Talk a little bit about some of the characterization observations or prep we've been doing for this. So we've been doing a lot of thinking in NIRCam about how do we prepare for exoplanet observations and what do we expect to see when we get up there. We can figure out, from photon noise expectation, what are the sort of uncertainties we expect in these observations, but there are a lot of detector effects that we need to account for. There are a lot of other systematic effects that are present, that we know are present on the detectors. And so we did these simulations. We simulated GJ436 and LS43, roughly speaking, and injected fake transmission spectra and then tried to recover them in an internal data challenge that we ran last spring. Thankfully, our internal analysis recovers the transmission spectrum correctly. We got uncertainties of about 30 ppm at a resolution of 100. That's about what we expected. It's a little higher than just predicted by photon noise. What that means is that the systematic floor due to detector effects appears like it is about 15 parts per million. That's a little bit dependent upon what spectral resolution you're using. At wider and lower spectral resolutions, where you're averaging over more pixels, those systematic effects are averaged out a little bit better, the noise floor goes down. But at our nominal observing resolution of about R of 100, we get a noise floor of about 15 ppm. And that appears to be independent of brightness as well. We get the same result at brightness of J of 8 as a brightness of J of 6. That's about, for reference, that gives us, for these observations, for the J of 6 observations, that gives us about 1.2 times the photon noise floor once we add these in quadrature. So 15 ppm, that's actually about what we expected. We expected a noise floor of about 20 ppm. So that we're doing a little bit better at the moment than we expected, but we're going to have other effects actually on orbit that are not just detector effects once we get up there. Okay, so what will we actually be able to do with JWST? So one, we expect JWST to give us beautiful bulk abundance measurements. So this simulated data on the left is from a white paper that Tom Green led about JWST observations of exoplanets. So it covers a range of instruments. You can see compared to the Hubble observations, so if you look at the corner plot down at the bottom there, Hubble gives us a rough indication of what the metallicity is. It gives us a rough indication of what the C to O ratio is. Jwst observations are going to be able to nail the bulk metallicity and nail the C to O really to the wall. And thinking about planet formation, right? So when we're talking about planet formation in the intro, I showed this plot of mass versus bulk metallicity. We're going to be able to get very good bulk metallicity measurements for these exoplanets as a function of mass. So we're going to be able to really well populate this diagram at a much higher precision than we've been able to do to this point. We're also going to be able to get very good elemental ratios. So this, from the left, is a simulation of one of our NIRCam GTO targets. Really, this was meant to exercise the analysis pipeline, but we get out elemental abundances out the other side from our full simulation. And again, you can see we measure water, we measure methane, we measure NH3, and we measure C to O. We're getting all of the major oxygen, carbon, and nitrogen bearing molecules in this atmosphere, and we get some information about the hydrogen content, right? So we can place, for this atmosphere, we could place points on this diagram, this solar system diagram, and really get good elemental or abundance ratios and use that to constrain the planet formation history of these planets, right? From the bulk abundances, we can try and constrain the overall formation pathway. From these elemental ratios, we try and constrain where did we form in the disk. So you can see this. This is a nice paper from Madhu that worked out different signatures of planet formation. So on the right, this is where do I start in the disk, and showing you tracks through the disks as the planet evolves. And then on the left, it's showing you the outcome O to H ratio and C to H ratios for these different planetary formation tracks. And you get different O to H ratios, you get different C to H ratios, depending upon what track you were on, whether or not your core is eroded or not. But the point being is that we'll be able to put points on this plot with these JWST observations, and the precisions will be good enough to identify what sort of track, given the disk properties, assumed disk properties we took, to try and recover that and learn something even about core erosion or not. So we're really going to get much better constraints on overall planet formation pathways and what happens during the planet formation process itself. Okay, we're also going to think about looking for habitable exoplanets. So I will say, I think probably a lot of people on this call now know this, that biosignatures on Earth-like planets are going to be difficult to do with JWST. So right now, of course, the best target we have, TRAPPIST planets. This is TRAPPIST-1e from a paper by Jacob Lustig-Jaeger. So these data, right, you could start identifying an Earth-like atmosphere, those two blue cases, but that's for 50 occultation events or 90 occultation events. You would need to spend a lot of time on the TRAPPIST system to be able to identify an Earth-like atmosphere. So I'm not saying it's impossible, but that's going to be a big ask for the TAC. We need to be very confident that we would get a useful result out of that if we wanted to do that. And TRAPPIST is really the only system right now that we could meaningfully think of doing this. But what we can think about doing is instead looking not like Earth-like planets, but looking at super Earth planets and quantifying the overall potential habitability, right? I said at the beginning that I would say even now we don't well understand why, say, Venus becomes Venus, why Earth becomes Earth, why some planets become habitable, why some planets become infernos or airless rocks. I think there's a lot of work here to be done on just evaluating the overall potential habitability of super Earths and maybe Earth-sized planets, and just sketching out that parameter space. What is something that roughly looks like the Earth? What is something that roughly looks like a rock? What is something that roughly looks like Venus? One particular thing that we could look for more directly for potentially habitable planets are planets with some sort of hydrogen atmosphere. So these are super Earth planets that are much larger than the Earth, and they have some residual hydrogen atmosphere, and that hydrogen atmosphere keeps them warm enough that they also develop a liquid water ocean. And you could see spectroscopic signatures of this relatively easily with JWST. You could determine if a super Earth in this plot has a massive H2 atmosphere and really, some sort of supercritical water and then rock, or if you have a smaller H2 atmosphere that allows you to form liquid water ocean, and then some interior there. The idea being that it's perfectly possible to have life form in a liquid water, one of these temperate super Earths with a residual hydrogen atmosphere if there's a large liquid water ocean. One term that's been suggested for this is Hysean planets. So these are planets that have water-rich interiors and oceans underneath hydrogen atmospheres. There are a lot of possible targets for these observations. There are a lot of planets that fall within the expected mass radius range to allow for this sort of scenario. And another advantage to looking at these sorts of planets is that it's possible that the Hysean habitable zone, as opposed to the terrestrial habitable zone, extends for a much wider range of parameter space because you have this hydrogen atmosphere that's able to maintain the surface temperature at temperate conditions. You could have a much wider range of parameter space, both in terms of planets we know about and planets we know about that are still in the habitable zone that you could meaningfully do a survey for potentially habitable planets here. Because these planets are larger, it also means that we can do a meaningful survey for potentially habitable Hysean planets using a reasonable amount of JWST time. So these are 3 different possible targets. All of these are showing simulated observations using only 1 to 4 transits of JWST. That is a reasonable ask to make for attack. We could go out and we could look at, say, TOI 270 with 3 transits of near spec or near cam, and we could make good, meaningful abundance measurements of methane and water and NH3 and all this other stuff, and determine if it's one of these Hysean planets that might be potentially habitable and might potentially have life on it. Okay, so I want to wrap up just quickly with thinking about how else we can look for life, because a lot of when we think about habitability and searches for life, what we think about is biosignatures. We think about looking for oxygen, maybe a little bit of methane. We think about looking for biological signs of life. And a lot of the development of techniques to characterize exoplanet atmospheres, particularly in the future, are designed around these searches for biological life. But I would say that in addition to biological evidence for life, we can also look for technological evidence for life. We can look for technosignatures. And in the last couple of years, particularly as biosignature searches have advanced, technosignature surface searches or theorizing about them have really been put on a much firmer, I would say, physical footing than they have in the past, right? This is thinking about what are the astrophysical signals we would search for if we wanted to search for technosignatures. What are concrete things we could look for that we think we would see in these atmospheric characterization observations? So one thing, could we detect industrial pollution in an exoplanet atmosphere? We've been talking about measuring abundances. Could we measure the abundances of, some sort of industrial pollution? So nitrogen oxide pollution, that's a major component of smog here on Earth. That might be detectable from JWST or OST, one of the next gen IR space telescopes, but it would be difficult. You really probably need OST to do this. Doing it with JWST would be extremely difficult. One thing you could do, this is a recent paper from Jacob Hack-Misra, is look for CFCs, right? CFCs have no natural source that we know of. They're produced in Earth's atmosphere by industrial activity. If CFCs were present at, say, 5 times the concentration they are on Earth, and they're present on TRAPPIST-1e, there's some industrial civilization there that's really pumping these out into their atmosphere, we would be able to see it with JWST. Likely be able to see it, depending upon what you think the noise floor is for MIRI observations. But we will be able to detect CFCs with these observations. And the nice thing about this is that this really piggybacks on atmospheric observations that we would be doing anyway, to look for biosignatures, to characterize TRAPPIST-1e, to see if there was life on TRAPPIST-1e. So this is a very specific prediction for what this would look like, and it's very complementary to existing biosignature searches. Finally, a little bit more further afield, using next generation space telescopes like LUVOIR or HABEX, We could also think about looking for night side city lights. So the Earth's night side is not completely dark. We have cities, cities have lights. City lights are very spectrally distinct, at least sodium lights are very spectrally distinct emission signatures. That means that we can think to look for these emission signatures in the atmospheric characterization observations that would be necessary to look for biosignatures. Louvois and Habex have both had major parts of the reports devoted towards looking for biosignatures using direct imaging observations. Those same direct imaging observations at about the amount of time you would require to look for a biosignature would also meaningfully be able to detect city light emission from the night side of these planets. Now, there's the amount of city lights you would require varies. Probably the best target, if you were to build something like Louvois A, would be Proxima B, right? It's the closest potentially habitable planets. There you could detect something like 10 to 12 times Earth's cities, which roughly would be Earth in like the mid 2100s if current trends continue for urbanization. For other targets, you'd also be able to detect city lights, but at higher urbanization fractions. So technosignatures are also something that we can be thinking about looking for in the future. And a lot of work is starting to be put into this. There's the NASA Technosignatures Working Group, which has been constituted. And there are a bunch of us that are working on making good astrophysically motivated observational predictions for specifically what we would see as a complement to biosignature searches. Okay, so I will leave up this conclusion slide. I'm not going to read it for you. I will leave it up for you to read at your leisure, and I will take your questions. Thank you.
All right, thank you, Thomas. So now we'll ask a question for question. If you have any question, please raise your hand. I can see a lot of clapping hands. Okay, Megan.
Super cool talk, Thomas. I had one question. I wasn't able to catch the phase coverage on your Kelt-1 phase curve as it went past, but I was wondering if you have coverage of ingress and egress, and if you've thought about trying to do some sort of eclipse mapping to constrain the cloud coverage on the D side.
Well, let's punch back to it for a second. So the problem actually, oddly enough, with the Kelt-1 observations was that it's almost an integer period, an integer multiple of 93 minutes of the HST orbit. So no, we don't get good phase coverage on the ingress and egress. That would be an interesting project to do though. Whoops. All right. Well, I'll leave this up.
Okay, any other question? Daniel?
That was a very nice talk. Yeah, I
Thanks.
enjoyed it. I had I was wondering if you could elaborate a little bit on the interpretation of, say, C2 ratios in terms of the formation, models, mapping it back. You mentioned a study by Madhu, which is a very nice study, but I was wondering how much uncertainties we still have in terms of C2 ratios and their connection to formation, initial conditions in the disk.
Yes, so that's a good question, Daniel. I would say that I think there are decent uncertainties there, and I was sweeping a little bit of that under the rug because the problem is that you can construct this nice scenario where there are snow lines in the disk. You get water snow line, you get the C to O snow line, and depending upon where you form the disk relative to those snow lines, that sets your the C to O ratio. But we know in the solar system that there is, diffusion or material moves, around in those snow lines, and the snow lines themselves move as a function of time. So there's a bunch of stuff happening, I would say, simultaneously in a real protoplanetary disk that may not be captured in, some of these tracks. But what I would say is that right now, I would say that most of our understanding of all that simultaneous motion occurs from theory, right? Like modeling what's happening inside of protoplanetary disks and figuring it out. What I would be excited to see is once we actually start doing these experiments and trying to work this out, is like there's a scenario where everything works, right? And you get these nice C/O measurements, and we know roughly, general disk properties from all observations, and we can say, man, there's a one-to-one correspondence here, right? We can really nail these things to the wall about what's happening. And in that case, maybe it means we can constrain the uncertainties. We can say, no, the snow lines are really important. They're really, they really set where things are. Things aren't moving around too much.
Yeah, I think also, I agree with you. I think it may be also interesting to see C/O ratios, for example, for different planets in the same system, where presumably the initial conditions are similar. I think that can help also narrow down a bit the parameters.
Yes, I think that would be another super interesting experiment to run as well.
Right, Ben.
Hi, Tom. Thanks for this really nice talk. I have to say that until this very moment, I had never really taken the idea of searching for technosignatures terribly seriously. And so the plot that you showed about, how much more essentially times and current Earth level of illumination would be detectable was really kind of a surprise to me. Like I wouldn't have guessed that it was, nearly so close, so to speak. And so another thing that made me wonder about is the possibility of detecting a sort of massive use of solar power and the resultant conversion to infrared radiation. I mean, I know that there are a few people out there who have tried to look for Dyson spheres, which I've always thought was a little bit fantastical. But if you look at a much smaller scale, I'm not sure what having very large solar arrays would just look like. A little bit of a debris disk, or if maybe there would be something more specific that people could look for. So I know that's kind of a crazy idea, and you may not have thought about it, but I'm wondering if anybody is working on this.
Yeah, so I will say, just to your point about not thinking about technosignatures, I think that's generally true for a lot of people. Because if you'll note, all the papers I cited, mine and Ravi and Jacob's, are all from the last year and a half. There's been a couple of us that have been, the last 2 years really been pushing on, now that we're getting good at measuring atmospheric signals, what can we think about doing with this in a real, physically motivated way? Right, for solar panels, I know, I think Yasmin Blesick has looked at, different surface properties. Like if you had, large cities that were all made out of concrete, what would it look like from the reflected spectrum? So I can't think of it off the top of my head, but yeah, I know there are people working on just surface reflectance spectrums and what you get. And I suspect that a solar panel there would have very distinct, if they were significant, coverage fraction, very distinct reflection properties in, say, direct imaging observations with WAR.
Yeah, I was also thinking about, sometimes people have these what seem like outlandish ideas about orbiting solar panels. And, perhaps, I mean, it might seem outlandish now, but perhaps to, in like a few hundred years, which isn't that much time in astronomical terms, maybe that isn't so crazy outlandish. So then that modifies probably both the absorption and transmission spectra that you see from the star.
Yes, I think you're right. It probably would.
So next question's from Eric.
Hi, Thomas. Super interesting talk. This is really exciting. This is a little bit of a follow-up on Daniel's question about C/O ratios. So you showed that really nicely with the super Earths, you can get good H2O abundances, good CH4 abundances. Looked like CO itself was a lot tougher. And so I was wondering, so those are individual molecules. What are your error bars, simulated error bars on the C/O ratio itself?
Well, one, hey, Eric, nice to see you. Yeah, so that's a good question. So I'll say I was sort of picking and choosing, like the plot I showed. Let me punch through, right, in this one, right? We don't have a good C/O ratio measurement. Well, this is why I'm doing the dry run of this talk. I agree this isn't a great plot for this. So what this is pulled from is this is literally like the simulation we were using to exercise our GTO observations. And this is very dependent on the injected transmission spectrum that we were seeing. So two things. One, the C to O ratio, I think, in this atmosphere is pretty low, which means if you don't have an absorption feature, it's hard to measure. Two, here I was just working on the shorter wavelength NIRCam observations. We're also going to be doing, for most of these targets, we're going to be doing longer wavelength 4 to 5 micron observations that then do have the major C to O absorption feature. So if I were to analyze that data set that I have sitting in my computer, I would expect in conjunction we'd get much better C to O measurements. So what I'm saying is I wouldn't, the error bars here for C to O are pretty bad, but my expectation is that generally we can probably, I would say we could probably expect for a broader wavelength coverage to get C to O measurements, hopefully to 0.3, 0.2, maybe even 0.1 dex for most good targets.
Cool. Okay, that's exciting. Thanks.
Yeah.
Okay, Sarah, please go ahead.
Hi, it was a very cool talk, so thank you. There's kind of this thing that's bothering me, and it's possible that I'm misremembering numbers, but you talked early on about cloud variability being small enough that it's not going to be an issue until you maybe push down to tons and tons of observations. And then at the end, when you're talking about these signatures of technosignatures, they also are small enough that we're going to need, again, hundreds of hours of observations. And so I wonder if those two things coupled are going to wash each other out. And just like kind of what you think about that, or if maybe I've got the orders of magnitude off.
Yeah. So I may have been a little imprecise. I think from Matt's work, what we can say is that we don't see any variability at the precision that Spitzer can measure it. Okay. Which is a very distinct statement, right? One of my actual concerns is that, so that means that broadly speaking, there doesn't seem to be, there was a scenario where we did see variability, right? And even at the Spitzer levels, things are really bouncing around. That's not the case. But I think there should be concern in the back of everybody's mind that at the JWST's precision, that we will see significant variability on at least some targets. And that means that we're going to have to do a couple of repeat observations on some of these targets to figure that out. Because if we just look once, we're never going to know. So I think you're exactly right. I think, and particularly for Earth-sized planets, if we're looking at technosignatures on Earth-sized planets, if there's cloud variability, like for the city lights, I was assuming there are 50% cloud coverage, but if you get a particularly clear day for some reason on one hemisphere, that whole thing may pivot up, it may pedestal down. Yeah, I think at the precisions we care about going forward, I think we're going to have to redo those experiments all over again to satisfy ourselves that it's not going to be a major issue, or to figure out that it is something we need to worry about.
Thanks.
Mm-hmm.
Ilaria, please go ahead.
Hi, Tom. Thanks for the nice talk. I wanted to ask about, again, the elemental ratios that you think you can infer from JWST. At least for disk observations, I know that all these ratios, carbon to hydrogen, oxygen to hydrogen, even C2O ratio, they depend very strongly on the assumed model that you use for retrieving then those abundances. How is that with exoplanets? What are the uncertainties there?
Laria, man, you're really going to make me pull off the curtain on exoplanet modeling. So yes, so very editorial comment. Well, I can say this because I'm an observer. I think that present exoplanet atmosphere observations are not terribly good for constraining a lot of those model uncertainties. And I think that to date, we've swept a lot of those uncertainties under the rug because the data hasn't been good enough to test them. My personal prediction is that particularly in the first year of JWST observations, I think that we're going to get some, I don't want to say a lot, but I think we're going to get at least some papers that claim very peculiar chemistry and very peculiar abundance measurements, because they're not going to account for some effect that we haven't had to worry about to date, right? They're not going to account for, two-dimensional effects across the day side. They're just going to model it as a 1D temperature pressure profile. And it turns out at the precision we care about, you can't do an entire integrated day side on as a 1D feature. So I think that's very on point. I will say that I think we're not really going to have a good sense of what's important and what we're missing until we actually start doing this. And I think the first year of observations, I think, is going to be very revealing. And I think that a year or two from now, we're going to have much better exoplanet atmosphere models than we do presently, and have a much better understanding of what's important and what's not, which frankly, I think should be very exciting to all of us, right? Because there's all this stuff we don't know. And man, I think we're going to be forced to know it in a year or two.
Thanks.
Okay, thank you. Any other question? Okay, Daniel, again, yeah.
Thanks. So Tom, just to follow up on this question. So I was wondering, what is the best way to convey this kind of systematic uncertainties that may exist in the models, right? I mean, you mentioned that you expect changes in the chemistry, and if we show, for example, a posterior distribution that suggests that we have a certain precision for a certain molecule, but I think it is inferred, right? It's under the assumption that we have a correct and complete model. And I'm wondering what's the best way for us to convey the uncertainty somehow, or to constrain what is the level of accuracy that we expect for the models.
That's a good question, Daniel. I've never actually thought about that. I mean, off the top of my head, I think maybe we run multiple sets of models. We have, like, to pick on Mike Line and Madhu, right? You get Mike Line and Madhu to sit down and run their own models, and then they both come back with slightly different answers. That gives you some sense of it.
Yes.
You could extend that also to thinking about, like, cat things, 2D, trying to do multiple 1D things across a day side to see what happens. Maybe that's the best way to do it. That's a good question. I don't think I have a good answer.
I'm thinking on, like, the methane, right, abundances that were revised about 6 years ago, and many of the results changed. And as long as people have shared assumptions, that will introduce systematics, and they may find results that agree, but it doesn't necessarily mean that they are right. But you are right that the more data we have, the more opportunities we have to test the models, the more confidence we have in them. But I'm just not sure what is the process to quantify that.
Yeah, I'm not sure I have a good answer either, Daniel. We should think about it.
Okay, excellent question. And okay, now if there is no other question, let's thank Thomas. You can all unmute and you can show your video, and then let's thank Thomas. Thank you for exciting talk.
All right, thank you guys.